All right, we are in day one. What we're going to do to start out this quarter is Math Week. Okay, and what we're going to do is we're just going to kind of go through all the math that we need to survive this quarter. And there's a fair amount of math, but here's the thing about it. The thing that I want you guys to realize is that this math, while it looks really daunting on the surface, is actually just a bunch of calculator buttons that you're going to press to get an answer. Okay? Thank you for that. We are not mathematicians here. We don't claim to be. We don't really want to be. I don't really mind math. I like math, but for most people, math is a four-letter word. So, you know, we're going to make the best of it. We're going to get the tools that we need to get these problems that we're going to solve. But let's always keep it in perspective that the math is not the focus of the course, even though it's going to be the stumbling block for most people. Okay? So with that in mind, we're going to talk a little bit about space, which some refer to as the final frontier. For us, it's going to be the initial frontier that we're going to talk about. So if we talk about a cube of space, like so, I'm no artist, we already know that. But if I talk about a cube full of space, it's clear that there are three dimensions. X, Y, and Z. X goes in this direction, Y goes in that direction, and Z is an arrow that comes out of the board towards us. Okay, it's kind of hard to draw that, but you might draw it this way. Each one of these is 90 degrees. So they're crossed in all dimensions. And this is the way we generally view space. We view space generally in what we call rectangular coordinates. And this is what we're most familiar with. If we look at an Excel spreadsheet has A, B, C, D, E, and 1, 2, 3, 4. And this cell right here is C2. Okay? That's what we call rectangular coordinates. It's in 2 dimensions, not 3. We can have multiple sheets in an Excel document, which in a sense gives us that third dimension. If we look at those sheets as coming out of the board, we can establish data in 3 dimensions if we want to. But for us, we're basically looking at a distance in this direction and a distance in this direction. This being X and that being Y. Okay? That's what we refer to as rectangular coordinates. When we look at Tacoma, we're at 12th Street, and what is this, Yakima? And we're right about there. We have an address that's based on an XY system. 12th Street, 11th Street. Okay, this might be 3200, 3300 moving in this direction, 12th, 11th in this direction. So when we look at addresses, we're always talking about rectangular coordinates. Okay? The reason for that is when we go from one place to another, we generally start out, say here for example, and we go +1 in the Y or in the X direction, and then maybe +3 blocks in the Y direction, X then Y, to get to the point where we want to be. So when we drive, when we look at Excel spreadsheets, when we look at most things, we try to look at them in terms of a square. And a square has 3 planes. Okay? And this works fine for us. It works fine for our way of thinking. It works fine for the fact that we use automobiles to get around. And our cities are laid out as grids, just like an Excel spreadsheet. But here's where the problem comes in. That works great if I'm a human, but what if I'm a crow? What then? If I'm a crow, and I'm sitting over here on this building, do you really think that I'm going to fly down this way and then fly up there? As a matter of fact, they have a term called "as the crow flies." When the crow goes to this point, it's going to fly in a straight line, and we're going to assume that the buildings don't matter. As the crow flies, ACTF. As ATCF, as the crow flies, is a direct path. Okay? And as such, if I were the crow, what I would do is I would look down that street and say, okay, I need to turn to an angle of so-and-so and travel for a distance r. And that will get me to the same point that I got to by going 3 blocks north and 1 block west or east. You see how that works? Same point. And the difference here is that when we look at something like angles and radiuses, which is what R stands for, we're clearly not talking about a square anymore, are we? We're now talking about what we refer to as polar or spherical coordinates. Okay? Polar and spherical coordinates is where everything is enclosed in a 3-dimensional sphere. And from the center point to any point in the system, we can establish an angle and a radius. And from that, we can define any point in that entire system. As a matter of fact, we have 2 different angles. We not only have the angle going up this way, but we also have the angle going this way as well if we're using 3 dimensions. We're lucky because we only have to use 2. So we don't need to worry about what comes out of the board and goes into the board. All we have to worry about is the footprint, the 2-dimensional footprint that's on the board. And we should already be familiar with that idea, because when we looked at a sine wave, like so, we decided last quarter that a sine wave was really nothing more than this. A circle with a certain number of degrees stretched out like a spring. And when we look at that in 2 dimensions, it turns into this. So we're kind of already used to visualizing things, 3-dimensional objects in 2 dimensions. For us, with this, we are going to work within the rectangular coordinate system, and we're going to work within the polar coordinate system. Those are the 2 things that we're going to work with. Another name for this is the Cartesian coordinate system. It's named after a mathematician, French guy named Descartes, who's dead now, but his legacy lives on. Okay? Questions? All right. Let's move on to page 2. One of the plans that we have in working with local fire departments is the use of drones to go out and scout the fire before the truck gets there. One of the ways that we can do that is fire department is here. The fire is here. When the dispatch call comes in, the fire department gets in their little trucks and they drive using the coordinate system, Cartesian or rectangular coordinate system, to get to the fire. The drone, on the other hand, when the dispatch call comes in, flies directly there. Which one do you think gets there first? Sure, the bird is going to get there first. It leaves when the call comes in. By the time the guys are in the truck, suited up, ready to go, drone is already halfway there. It's traveling the most direct route, and the time differential between it and the fire truck getting there allows for the drone to be able to beam back pictures into the truck itself somewhere around here, so that the fire department knows what's going on at the scene, where to park, where there may be a need for additional units or police support or something. They can get a better idea of what's going on at the scene. And we take advantage of the fact that a polar coordinate provides a shorter route to a point than rectangular does, generally speaking. Okay? So this has applications outside of electronics, as most things that we talk about do. It's good to recognize that from time to time. When we talk about the system itself, we're setting up a set of coordinate axes, and we're going to do this in 2 dimensions rather than 3, since that's what we're going to be limiting our use of this math to. So we may as well just stick with 2 dimensions. Here's the intersection of x and y, and the point in the middle has a name. It is called the origin. It is at 0 on the x-axis and 0 on the y-axis. Okay, maybe some of this you've heard before. There's some terminology that we'll go through here. Maybe you've heard it before. Hopefully it's like getting back on a bike and it's like, oh yeah, I remember when I see x comma y in parentheses, that's an ordered pair. X is what we refer to as the domain, and y is what we refer to as the range. When we looked at the oscilloscope last quarter, we used this coordinate system in the scope. This was time, and this was voltage. So this is a plot of, would be a plot of a voltage in the time domain. And at any particular time, we could identify what the voltage is at that time. That's the way we generally read an oscilloscope. Less frequently do we say, at what time did this voltage occur? Normally, the x-axis is what we call our domain. That's our reference. We're looking at a particular time and then looking to see what the value is at that time. Do you see the difference between those two things? Okay, so when we look at this, this is an example of the time domain in the rectangular or Cartesian system. Clear? Are we clear? X, Y, origin, and we're going to draw a circle. And the circle has a radius of 1. This is 0 degrees, this is 90 degrees, this is 180 degrees, this is 270 degrees. And this represents our sine wave. Circle. Starts out here at 0 degrees and goes around in a circle. Can you see the beginning of it right there at that end? It starts right there at 0 degrees and looks like this. Here's the end. Around in a circle we go. Now, when we look at an ordered pair, we should be able to write down the value of the ordered pair at 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Okay, that being the case, what is the ordered pair going to look like at 0 degrees? Remember, an ordered pair looks like x, comma, y. And what is that going to look like for us? How far is this point in the x direction and how far in the y direction? What do you think?
1 and 0.
1 in the x direction because we're out at a radius of 1. But we're on the x line, which means we're not up or down, which means in the y direction, we're still at 0. Yes? So it should be 1, comma, 0. At 90 degrees with a radius of 1, we're pointed straight up. Looks like 0, comma 1 to me. Yes? What about 180 degrees?
-1, 0.
We went back 1 from our origin, -1. And we're on the x-axis, so the y is equal to 0. And at 270, using the same format and the same idea, we should have 0, comma, -1. 0 in the x direction, 1 down in the y direction. Questions? Have you seen this before, Raymond?
Nope.
Good. Does it make sense to you?
I'm catching on.
Okay. We come up with separate or special names for these numbers that happen at the axes. And this is where we start to get into things like trigonometry, and that's really going to be the focus of where this math is going to go. We're going to start looking at points around this circle, and we're going to establish that that point is a certain distance x and a certain distance y, which is equal to a radius at an angle.
So is that what that little fish thing means?
That's what that little fish thing means. It
means an angle.
It's an angle, yeah. We can use, and somebody made a comment, and I don't know who it was, but somebody had made a comment in the student satisfaction surveys that I gave out about the symbols in the book being different than the symbols that I used. And this is a perfect time to address that. I don't know whether it was one of you guys, and it doesn't matter because I see the point. It's one of the things that I probably will not spend a whole lot of time changing. And the reason is because you're not just going to see that in the textbook. You're going to see that with engineers. You're going to see that with everyone that you interface. They're going to use different terminologies and different symbols for the same thing. So it's it's just a picture. You have to deal with that. You have to learn at some point as you get more experience. The context of what's being said will give you the idea. If you see something like this and you learn that this angle was equal to alpha, which is what that symbol means, and you go to work for another company and you see the same drawing and they have something that looks like this, you have to be able to figure out that they're talking about the same thing. Okay, there is no standard for how we represent these angles in these, how we represent these angles in a lot of these quantities. Some are standardized, like ohms. It's always going to be an omega symbol. Most of these things come from the Greek alphabet. That's where most of these funky symbols come from. So if there's ever one that you don't understand, just ask. But even myself, I will use different symbols. Okay, it's one of those things that it really doesn't matter past a certain point, and most people that are out in the field are going to use what they were taught or what they learned, or maybe they don't like drawing that, they'd rather draw that. They like drawing little fishies, so they're going to use the little fishy. It's easy for me. It's one pen stroke. This is two. So, everybody has their reason. But nonetheless, yes, the little fishy, then the Greek letter there, generally is going to mean the angle between those two lines. Okay? Does that clear that up?
Yeah.
All right. We have special names for these. And I'm going to lead by example here and just write down what it is I'm getting at, and then we'll talk about it. Okay? Cosine and sine. So what I invite you to do is enter in a couple of these numbers on your calculator. Put in 180 degrees and press the sine button and see what you get. Put in 270 and push the cosine button. See what you get. I bet you'll come up with these numbers. if your calculator is set to degrees, which it probably is after last quarter. Let me help you visualize this. Let's say I have a room, and in that room I have a pole sticking up out of the corner. And I take a light bulb and I aim the light in this direction. When I aim that light, what's going to happen is that pole is going to cast a shadow this big. And that is what we're going to call the Y component. When I shine a light from above, it's going to cast a shadow this long. And that is what we call the X component. Here's our angle, and here's our radius. Guess what our job is going to be to do?
Find out what X and Y is.
If I know what the radius is and the angle are, I need to know what X and Y is. If I know what X and Y are, I need to be able to find the angle and the radius. Okay? That way, I can come up with the drone's instructions to fly to the fire. Once I know where the fire is, I can count how many blocks it is east and how many blocks it is north, and somehow, I don't know, use one of those push button funky little things that you come up with answers with and get a number for the radius and how far to turn the axis to make it go to this point. In other words, what we need to do is we need to be able to convert between rectangular and polar coordinate systems. We're going to be doing that all the time. It's going to be a non-stop event this quarter. No matter what circuit we're working with for the next 8 weeks, you will be spending probably 25 to 35% of your time converting between polar and rectangular coordinates. Doesn't that sound like fun?
Not really.
No, but it's just a bunch of buttons on your calculator. So, you know, we're going to distill it down to that process because it's not the process itself, it's what we use the process for that matters. So that gives us license to kind of label that process and say we're just going to do this every time and this is how we're going to do that conversion. So we're going to learn that conversion today, and that will be it for this morning. Again, it's very mathematical, it's very button pressy on your calculator, and it's going to be good to do this a number of times so that we can learn to estimate our answer before we press the buttons so we can figure out if we press a wrong button. It's always good to know what the answer looks like. In other words, you should always know the answer to the question before you ask it when it comes to mathematics. So, let's look at a single point in space right here. And that point is going to be 4 in the x direction and 3 in the y direction. And what we want to do is we want to figure out what r is and what the angle is. Okay, it's time to get your calculators out. R is going to be equal to the square root of x squared plus y squared. That's the Pythagorean theorem. That tells us if we square x, square y, and add them together, and then take the square root, we will get the value for r. And this is from Pythagoras. So in this particular example, r will be equal to the square root of 16 plus 9, which is equal to the square root of 25, which is equal to 5. Got that? All right, now there's another formula that we need to use, and this is one of those things that you may remember from primary or secondary education or something about SOHCAHTOA. You ever heard of SOHCAHTOA before? SOHCAHTOA. That's one of those things that helps you remember 3 formulas. The sine of the angle is equal to the opposite over the hypotenuse. The cosine of the angle is equal to the adjacent over the hypotenuse. And the tangent of the angle is equal to the opposite divided by the adjacent. The one we're going to use is this one. The tangent of the angle is equal to the opposite over the adjacent. And we could go through a whole bunch of falderall and figure out why that is, but at the end of the day, like I said, it's just a formula we're going to plug in to get an answer. So we don't care about where the formula came from. Just like I don't care about the guy that annealed this or made it. It's a frickin' valve. I bought it to replace another valve. I don't care who made it. I don't care what it came from. All I care is how am I going to use it. And the same thing is true with these formulas for us. Okay, the unfortunate thing about this is that the angle is the unknown. We already know the opposite. When we look at this angle here, all the way across the triangle from it is the opposite. The one that's part of the angle is the adjacent. And the long one that stretches between the longest of the 3 is what we call the hypotenuse. Okay? So in this case, let's replace these with some numbers. The tangent of the angle is equal to the opposite, which is 3, divided by the adjacent, which is 4. Now if you remember what we did last quarter and since the beginning of time, we've always kind of used the equal sign as a fulcrum and said that anything I do to one side, I have to do to the other in order to preserve the equality. Remember that discussion? So what we're going to do is we're going to take the inverse, or the inverse tangent, of both sides. And of course, as if by magic, the inverse of the tangent times the tangent itself, anytime we invert something and multiply, they cancel each other. It's like 1 over the tangent times the tangent is equal to 1. So these cancel each other out, and we're left with the angle is equal to the inverse tangent of 3/4. Or the inverse tangent of 0.75. In your calculator, put in 0.75, hit the shift button, then the tangent button, and you should be there.
What's that, 0.75?
0.75, shift, which is the green button,
Second.
and then tangent. What'd you get?
36.86.
So that means our angle is equal to 37 degrees. 36.86 degrees. That's what we calculated. Enjoy this aggravation, because tomorrow, chances are, I will show you the simple way to do this that doesn't involve any of this. But in order to have license to use that, I'm going to make you go through this. Okay, so given x and y, I can now calculate the radius, which is using the Pythagorean theorem, and I can calculate the angle using the SOHCAHTOA, just specifically the TOA part. And I can come up with an answer. Questions?
The triangle with the line over it there, is that just like a teeter-totter? Is that an example thing?
That's what we used last quarter when we talked about math in the beginning. We said that equations are like a teeter-totter, and that if you feed one baby a pizza, you got to feed the other baby the same amount of pizza to keep it
balanced.
Yes. So everything we do to one side, we took the inverse tangent of this side, then we took the inverse tangent of the other side. Good. Are you good with that? Okay, good deal. So we have a couple of equations. This one and this one. The angle is equal to the inverse tangent of y over x. And we use these to convert from rectangular to polar. Now, let's take the same numbers that we had before and see if we can get back to, what did we have? X equals 4 and y equals 3. Isn't that what we originally started with? Can we get back to that? And the answer is yes, we can. Here's the simple way to do it. X is equal to r times the cosine of the angle. Y is equal to r times the sine of the angle. Remember, the x is the cosine direction and the y is the sine direction. Look back at your ordered pair pictures and you'll see.
So that would be polar to rectangular?
This would be polar to rectangular. We were given the angle and the radius, and now we have to come up with x and y. You remember when we looked at a circle that had a radius of 1, x was equal to the cosine of the angle and y was equal to the sine of the angle. You remember we went through that? That's why I had you go through those. Now, since we're looking at a circle with a radius of 5, everything's going to be multiplied by 5. And if you plug those numbers in, and I will allow you to do that on your own since we're running short on time, you will come up with roughly 4 and roughly 3. I say roughly because this was actually 36 point something, so it was a little bit, I've rounded a little bit, therefore these won't be exactly 4.00 or 3.00.
So when you put that in there, you hit, say,
Enter 37, then sine
and then times r?
times 5 equals. Try that, see what happens. Put in 37, hit the sine, times 5 equals. What'd you get?
3.009.
So 3.01 roughly, 3.
Yeah.
Okay, so that works.
So
and if you
that
do-
was my question. You put the angle in, then you hit the sine or cosine key,
Yes.
and then you multiply.
Mhm.
So you work it from the right in.
With your calculator, yes. I don't know how yours works. It's for you to discover.
I think it's the same way.
Is it? Some work that way. Some of them you put in the sine first and then hit the 37 and then it gives you that number. It all depends on how your calculator works. That's something you gotta come to grips with. You have the same one I have, so we'll be fine. You and I will be fine. You're gonna have to figure it out on your own unless you have that calculator. So, but it shouldn't be a problem once you get it set up right. It's just a question of plugging these things in. Okay, so we can convert from polar to rectangular and rectangular to polar. Polar to rectangular, x is equal to r times the cosine of the angle, and y is equal to r times the sine of the angle. Two simple ideas. Okay. That concludes day 1. Questions? Anything that we did that you want to go over? Does it look good?
No, so far I'm tracking. So far.
Tomorrow we'll do some examples
Okay.
and dig into this a little bit because we also have to deal with addition and subtraction, multiplication and division of these numbers. Okay, in other words, I may need to divide this divided by that. What's that going to equal to? Maybe this is 5 at an angle of 36.7 degrees, and this is 12 at an angle of 194 degrees. Divide them. Add them. Multiply them. That's what tomorrow we'll be doing. See if you can wrap your head about the idea of dividing arrows. But that's exactly what we're going to do. Remember, they're just quantities. Okay?
Sure.
All right, that's it for today. See you all bright and early tomorrow morning.
Yay.
Yay. Start, stop.